Hello everyone, welcome back to the new video. So today in this video we'll be going through this very interesting paper which is titled as BERT Goes Shopping, Comparing Distributional Models for Product Representations. And this is from researchers from Bocconi University and Covio AI Labs. So at very high level, the intention of the paper is to compare distributional models that help us get the embedding representation of any granular object that has a substantial meaning in the underlying corpus. So in this paper, authors primarily do a comparison between the BERT-based, which is a transformer-based embedding representation, and the traditional ways, which are word-to-vec and glove, for learning the representation of products that a user goes through during any given surfing session. So with that said, let's start with the abstract. So they say word embeddings have been successfully applied to e-commerce products through prod-to-vec. So prod-to-vec is a word-to-vec based embedding generation method that tries to model a given product in a certain context with a dense vector representation, where again the underlying assumption is that a given product can be thought of based on the things that occur to its context, or in other words, the products that have a similar search pattern or search history are likely to be the same products. So with that thought in mind, the word-to-vec is applied to a chain of all the products that have been searched through in a given session, where now each of the products can be thought of as a word unit in a sentence, and then you apply word-to-vec to get the embedding representation for each of these units, which are nothing but products. So this is one of the ways that people have been doing it. But again, recently one of the papers that I have done on this channel, which was BERT for Rec, that used BERT for learning a contextualized embedding representation for every product in the search lineage in order to facilitate better recommendations. So the focus of that paper was to primarily apply BERT for such tasks, whereas in this paper we'll see a comparison to in what conditions do we have prod-to-vec working better than BERT-based architecture for learning these representations. What is the trade-off in terms of time, how much data would you need, and what are some other practical considerations that you should keep in mind while choosing either of these methods. So yeah, that's what they have also written. Through extensive experiments over multiple shops, different tasks and range of design choices, we systematically compare accuracy of prod to BERT and prod to vec embeddings. So yeah, that's the main idea of the paper. So let's move forward and see rest of the details. So for getting the BERT-based representation for each of the products, they trained their model and named their work as prod to BERT. And the training is done in a typical fashion to how the BERT works, but just only the MLM part, which is masked language modeling. So if you see this figure, the idea of MLM is to take a sequence of tokens, P1 to P3 for example, where some percentage of the intermediate tokens would be replaced with a masked token, which will then be augmented by its positional embedding, passed through certain number of transformer layers, which are composed of multi-head attention and feed-forward neural network. And at the output end, you'll have one representation per input, where at any given time you'll be predicting what is that word that can be placed against this masked token. For that, you add a classifier, do a softmax, you get a probability distribution across the entire vocabulary, and you choose the word that has the highest probability. So this is what we call as MLM, masked language modeling. Although the original BERT was also trained with another objective, which was NSP, which stands for next sentence prediction. But again, for this use case, where we want to get the representation of every product given the search sequence, MLM was enough. So yeah, so what they do is, every session is now composed of a product that the user searches. So let's say if I search for product number P1, P2, P3, and then P4. So let's say this is one of the session. If I log into my Amazon account or any of that account, and these are the products that I searched through. So this is my search history for that session. So they treat every session as a sentence, and each of these units, which are these products, as words in that sentence. And now the idea is same. You pass them through BERT, and the output end, if let's say this was masked, you try to predict what this word or the product was. And you keep iterating this for n number of sentences, and also through the duplicate instances of the same utterance. So that way you also capture the sentence level diversity in terms of the masked token. So if you see this figure again, let's say the first thing that you search for is the boots, then football, then gloves, and then jersey. So this is what they call as telemetry data. These are the products that you had gone through. Now for transforming this sequence into the training data, you just mask some random 15 to 10% of the words and replace them with the masked token. And this is what the sequence now you have. And typically you will find these sequences to be evolving over the intents, where the initial ones would be with the intent of exploration, and as you proceed towards the end, the chances are high that the intent has now changed to purchasing that product. So that way the sequentiality is still maintained, just like what happens in a sentence flow. Cool. And once you have many of these training instances, you train your BERT model with the MLM objective, which we had discussed earlier. Okay. So now the authors talk about the hyperparameter and design choices. So under this section, they discuss many previous existing literatures around how the number of layers affect the accuracy after a certain point. And also, for example, let's say whether the use of duplicate data helps in better generalization or not. So as per Liu et al. In 2019, they found that if you augment the data to a certain number of time, which is 5 in this case, the first thing which is obvious is that it gives you more data. And with that, it also allows you to kind of mask different segments of the same sentence during the pre-training phase. So authors in this paper also try that. And apart from this, they also tune on other parameters such as epoch, layers, masking probability, as in how much percentage of a sentence would you put as a mask token, and do the prediction for that. And then the duplicate, which is a Boolean value, whether they should be duplicated or not. So they use prod to vec as their baseline method. So prod to vec, as I had already discussed, is trained with the continuous bag of words architecture with negative sampling over all the shopping sessions. So at very high level, the way SIBO works is, let's say if you have a sentence S that has these many number of words, 1, 2, 3, 4, 5 words, and let's say we want to get a representation for this. So we have a window length of 2, which is we'll consider 2 words to its left, 2 words to its right, and at the output end we'll utilize all these 4 words and make the prediction for the center word. So here you will have the softmax over the entire vocabulary, and based on how much you are close to the actual word, you'll back propagate and adjust the weights. So yeah, this is how SIBO would work, and negative sampling allows you to kind of put this target word in the context where it's not likely to occur. Cool. So talking about the dataset, author works with 2 datasets from shop A and shop B, wherein they collect the search logs for each of these shops that has around 5 product actions like detail, add, purchase, remove, and click. So both of these are like digital shops, where shop A is about sports apparel and shop B is about home improvement. And these are some of the statistics, like as in number of sessions and number of products that are listed over there. So apart from this, they also impose a pre-processing step where they filter out any session that's less than 3 or greater than 10, I guess. Once again, so yeah, greater than 20 interactions. So if the sequence length of interaction is less than 3, or if it's greater than 20, they eliminate such sessions. So yeah, that's about the dataset that they use. Then talking about the experiments, one of which what they do is next event prediction, where the task is to predict the next action that the user is likely to take given some previous actions. So it could be like, if I come to the website, I just explore, then buy, then explore, then buy, or maybe one of the actions that's again over there. So what could be the next action that you predict? So this is like the next event prediction. Based on the previous events, what is the next action that I'm going to take? So for prod to BERT, which is again a BERT-based architecture that we have discussed, they mask out the last element in every sequence, and which is what the BERT is supposed to predict by seeing all the sequence tokens that have occurred in the past. And at that Tth step, we pick the top k most likely action that the BERT says. So that's about prod to BERT. Now talking about prod to vec, which is a word to vec based idea, we have a sequence of this sort. Leaving the last one, we take the representation of each of these actions, then average them out to get a 1 to t minus 1 action representation of our session, which they then use and perform the KNN prediction to get the last item what is likely to be there. So yeah, these were the 2 things that they tried, and these are the results with respect to that. We can clearly see, based on different configuration for prod to BERT, almost all of them apart from just this one surpass the best models for prod to vec for both the shops by huge margins. Okay, and talking about the time it takes and the cost associated for training one of the model instances. So for prod to vec, the time took was roughly around 4 to 20 minutes, and the cost associated was $0.006 to $0.33, whereas which is very high in prod to BERT to 1200 minutes, and it costs you somewhere close to $48 to $250. So yeah, this is the trade-off that you get for getting the accuracy boost, roughly around 10-point increase. Okay. So apart from this, they did a second experiment, which is intent prediction, where the ultimate goal was to see if the shopping session is going to end in a purchase intent or not. So that's what we had to classify based on the representation that we learned for that session using prod to BERT or prod to WIC. So in this evaluation, they found a little discrepancy in terms of the performance which they saw in next event prediction, as in with various techniques to how did they get the representation for the sequence. For example, one of the ways they picked in the representation was from the very early layer from the BERT. Then the second was to concatenate embeddings that you get from every layer, then learning a function that would merge the embeddings from the last layer into one single representation, and finally adding an extra layer on top of the CLS vector and then fine-tuning the entire architecture. So all of these were the experiments that the authors tried in terms of evaluating the goodness of the representations. But still, if you see the accuracy numbers, prod to WIC gave us 0.558 and the best one from prod to BERT gave us 0.567, which is almost a negligible difference. But if you see the trade-off in terms of time and cost it takes to train prod to BERT compared to prod to WIC, clearly prod to WIC is the choice that you want to make, right? So yeah, that's the trade-off, and clearly I feel it's not really a confident conclusion in terms of whether prod to BERT or prod to WIC will show short perform better for a given task, because that's what we are seeing in the intent prediction task and the next event prediction. So one of the hypotheses that the researchers make in this paper is that probably the prod to BERT performs really good in NEP task, because the behavior of the task is more or less like MLM, where you mask out something and predict that based on other things that occur to its context. Although in MLM, apart from the cases where the last token is just masked, you consider bidirectional context for making this prediction. And in the next event prediction task, you specifically just mask out the last token and make prediction based on the tokens that are to its left. But still the idea is same, because in the original MLM training, the model would have seen such scenarios as well. So that's why prod to BERT performs better than prod to WIC for that specific task, which is unlike the case in intent prediction, because this is just a sequence classification task. But probably I believe if NSP was also tuned, which is next sequence prediction, apart from just the MLM, then we would have seen gain in the intent prediction task as well, at least for prod to BERT fine-tune segment. So yeah, I think now we're done with the paper. With that said, if you're new to this channel, make sure to hit the subscribe button and like this video. Also, if you're interested in getting one email per month for all the videos that I released for the previous month, there is a sign up link in the description box. Make sure to put your email over there and let me know. I hope it was a fun read for you as well. I'll meet you in the next video. Bye bye, take care, and Happy New Year to each and everyone.